Okay, we'll start with the introduction. So thank you all for attending. This is the, I'm not sure how many of these Applied PD seminars we've had this quarter, but we'll have a string of a few in a row right now. So this week's speaker is Alejandro Aceves from Southern Methodist University, where he is a professor and also currently the chair of the department. Alejandro got his PhD from the University of Arizona in 1988. And after a long stay, including a chairmanship at the University of New Mexico, he's been now at Southern Methodist for over a decade. He is an expert at using methods from perturbation theory, asymptotics, and others to, especially with applications to nonlinear optics. And I believe that is something that we'll hear about today. Alejandro has to leave a little bit earlier because he has to go teach a little bit later. So this will be a 40-minute talk with then about 5 minutes for questions. So thank you, Alejandro.
Well, thank you, Jorge, Bernard, for the kind invitation. And yes, if you see my eyes drop into the left and be down left, I'll be checking on the watch because I have to teach in the hour, at the hour. And again, grateful for the invitation because it allows me to also see some friends that had also emailed me about indicating their interest to come and give the talk. So in the spirit of being a PD seminar, notwithstanding in the Zoom version, I will present more as ideas rather than clean results and new things surrounding the modeling around nonlinear wave phenomena. Again, in my case, on the underlying motivation is in optics and photonics. And there are two elements. I put it in the title, twist. That means what happens when the medium of propagation is rotating in the direction of propagation. And the notion of non-locality, which is, it's a terminology that is understood in nonlinear dynamics, but a particular one that refers to what is known as the fractional Laplacian or fractional diffraction in the optics case. So as I said, I will talk about, I'll give basically more of an introduction and a couple of examples on these two topics. The concept of twisting in the direction of propagation, so it's kind of a topological feature, and the concept of fractionality as it applies to photonics. Briefly, a little bit of advertising with no apologies. We have what is called a research training group, NSF supported proposal, and we will be seeking for a postdoctoral fellow. I have to put the immediate disclaimer for this particular NSF program. The applicants should be US nationals, US green card holders, US citizens. And I want you just to see the bolded, what is written in bold as the areas of interest where we would be seeking fellows. Look for math jobs in the weeks to come for the way to submit applications. Please tell young people to consider this opportunity. So what is the well-known story for I'm sure all of us in the audience in the realm of the nonlinear Schrodinger equation. So if I were to characterize in the first equation the concept in optics, Z is time-like, it's a propagation. In optics, this Laplacian in transverse directions is diffraction. And then you have a nonlinearity. And the underlying general studies can be summarized or oversimplified if just for the for this talk in terms of the motivation, in terms of dimensionality, how many transverse dimensions, and the strength and the role of nonlinearity. So if we restrict the Laplacian operator to one dimension, we have the second derivative, and if we restrict the nonlinearity to the cubic nonlinearity, we have the integrable nonlinear Schrodinger equation. We call it 1 + 1, and everything really is known. The underlying integrability gives all source of results, solitons, and whatnot. The other one, the only other one I want to refer to is the case of 1 plus 2. So z is the direction of propagation, the time lag, and 2 transverse directions. And in this case, once again, in the context of the cubic nonlinearity, I want to highlight that the dynamics in this case is a dynamics of the one that is most known that accounts for nonlinearity and dimensionality is conditions for blow up in finite time, meaning that if you have a sufficiently energetic initial condition, in this case, a light beam that is confined and with enough power, the equation, and one way to characterize this behavior is by the so-called virial theorem, shows blow up in finite time. Obviously, if you deal with physics, you have to add other physics to see what arrests blow up. So these are the most known and understood, and around that there is all sorts of problems that have been studied under additional terms such as perturbations, in this case, additional terms that would arrest the blow up. In photonics, it is equally important to study models that intrinsically or at the beginning are best described as discrete systems of ODs. So an analogy here, an example here in which research goes a lot from our point of view of modelers, applied mathematicians, one of the relevant questions is always the validity of a continuum approximation and the intrinsic properties of highly localized solutions of the discrete model that depart from the continuous. So the most well-known is if I have in the photonics world an array of waveguides, uniform, equally aligned, and with nearest neighbors coupling, this is the model for propagation. N is the index of each waveguide and the electric field that propagates at each index, which at each waveguide, that means most of the energy is concentrated in the individual waveguides, leads to a dynamics that in what is called the long wave or the continuum approximation, once again, refers to solitons. And the concept here is that what is interesting in low energy, this is the behavior, the red spots are high energy of what you would think of as discrete diffraction. That is, what is the role of discrete diffraction if we neglect nonlinearity, and at high powers energy localizes. So I mentioned this because not only these are relevant if you want to model photonics, but it will have a connection with the second part of the topic. So the new things I want to introduce the audience, and I hope you find them interesting, and I welcome any feedback down the road or on your own research that may have triggered studying similar systems, is what happens if you twist the photonic structure. So think of the picture here as the cross-section of a photonic structure. For if you're not into photonics, is a profile that is periodic-like of index of refraction. So if we think about the linear case, this is the potential, and you have many modes. And typically in the simplest way in which optics and photonics works, we work around the fundamental mode, something localized at the core in the high index. But what if you have a rich photonic structure? Then you have other modes, for the so-called block modes. And you have a hierarchy of modes and a non-trivial dispersion relation. And in our language of applied mathematics, when you say what dynamical effect can happen is, for example, through resonances, coupling energy between different modes. So the picture here is if I were in the top, if I were to have a guided mode in the transverse structure, so this is the red spots, energy is concentrated in a few spots. It may be non-resonance or far apart from any other, so it's effectively uncoupled from the rest of the accessible modes, and it behaves in a stationary-like profile. But if the feature here is I'm going to twist the photonic structure, I'm going to put in Z, a Z-dependent behavior that is in a rotating way. And the rotation, what it does, an explanation, a hand waving explanation, is it distorts the mode of propagation or the eigenvalue, and you enhance resonances with higher modes, in particular, these beautiful profiles in which energy now is in the region far away from the core area. So this is the type of dynamics that the twisting creates, novel interactions between modes that are becoming of interest. If I were to talk about a discrete system, so imagine I have several cores in a circular geometry, and if in, again, here is a good picture of what I'm thinking about when you go in the direction of propagation. You're twisting collectively all these elements, and the discrete model that I presented before, the rotation creates a complex coupling or a phase, and through this complex coupling, you may distort the modes. In the simplest way, I'm going to just show a simple result of what we call localized modes. So imagine a case of 6 of these cores that are coupled, and then there is the rotation. So the rotation, the parameter that describes this twist of the multi-core element is this phase phi. So you can model as in an asymptotic way what I will call a localized mode. Localized mode is that in which, in the discrete models, most of the energy is carried in an isolated waveguide or core, and the rest have low energy. So the asymptotics here is the highly localized, another language that has been used in the anti-continuum limit. Imagine all the energy is effectively in one side. So this is the propagation in one side. C10 takes a very simple form. And then you can ignore nonlinearity in the other cores that allows us to solve in a hierarchical way the low amplitude side lobes in the neighbors. So this rho is a large parameter, and you could see indeed that as you move far away from the central core in terms of nearest neighbors, the energy goes like, the amplitude goes 1 over rho cubed. But the interesting thing that I want to highlight is the role of the phase. And in particular, in the case of that we have here with 6 cores, one of them has an amplitude that has the form cosine of 3 phi at leading order. And you could see that if I put a phase pi over 6, that becomes 0. So this is an interesting thing in optics. It calls topological defects or obstacles or dark spots. What you could not create in the untwisted mode, which is a core where the energy is all 0. Again, also in the physics language, you always have some sort of tunneling. The twist can allow you to inhibit tunneling towards, in this case, the 4 fiber. So this is just a not difficult calculation, but already showing some interesting features. And there are some references, I don't remember if I put them at the end on this particular topic, that talks about this concept of creating sites that you inhibit the access or the tunneling, creating dark spots. In my view, one of the most beautiful recent experiments was done by a group at MaxPlanck in Germany, led by Philip Russell. And he had again, what you see here is a cross-section of a photonic crystal. The light areas is high index, the dark circles is air. So in this photonic crystal, what the mode, when you solve the linear problem with this periodic-like structure, the mode is a block wave. And in fact, it is a block wave that, in terms of the analysis, is unconfined. So it extends. So it's not a guided mode. There is no guiding element in the structure that confines energy on its own as a profile of index of refraction. And that, the guided mode, if I look at the intensity, this is from the picture from the paper, if you look at, I seem to lose the arrow from the, oh, here it is. If I look at intensity, look at alpha, the parameter alpha is going to be the twist rate. So once again, the idea is twist this structure as I go towards the camera, the structure is twisting at certain rate. So in the absence of a rate when alpha is 0, the mode is an extended mode. And if I begin to twist at certain angular velocity, 1.26 radians per millimeter, then you begin to confine light. The energy is confined in a finite region, and the higher the rotation, the bigger the confinement. This is a numerical simulation. And so in this case, again, the role of the twist is to confine what would otherwise be a non-confined mode. And we were interested in trying to do some asymptotic, some analysis for motivated by this problem. So what I will present is a brief description just in the linear case, and not quite necessarily within the context of the specific parameters here, but we believe in principle it tells you the story or the explanation via asymptotics of this confinement. So beyond the specific result, I want, for those of you who work in this class of problems, to see firsthand what emerges from the twist. And some people call it a gauge. And a gauge could be viewed by saying, well, I have my linear Schrodinger equation. So the nonlinearity here is, you can add it or not add it, but the element of the mathematics behind the twist is more on the linear propagator. And you assume that the index of refraction depends on z, on the propagation direction, in the particular form of a rotation of this twisting. So if I were to do a change of variables and move in the rotating frame, so big X and big Y is the usual transformation of rotations, but now the rotation is z dependent, then this equation, as you, all of us know well, the Laplacian remains a Laplacian, but there is this added term. And now we have in this twisted frame of reference, we have the Schrodinger equation and plus this gauge. Here, the way it is written, this, and I apologize for poor notation, uppercase E is the electric field and the small e is epsilon. So I'm making a big jump. I'm just showing the highlight of the work. There is a small parameter that relates the alpha parameter and the intrinsic periodicity in the refractive index profile. So think of epsilon as a small parameter. And I want to show the role of confinement in this case. So once again, if the way it's written, the dominant term, as it's always the case even in weakly nonlinear theory, is to capture the mode. So now here is the mode, which are the second and third terms, is the eigenvalue problem for the Laplacian with a particular potential we call n effective. And in this case, once again, is the Bloch mode, because if I'm in the rotating, in the twist rotating frame, I always see this Bloch mode because the profile doesn't change as a leading order. So I call it B because it's the Bloch mode. And again, the point to be considered here is, think of this as an extended mode. And then in the asymptotics, in the modulation theory, we are going to prefactor it by an amplitude, a modulated amplitude, and a correction by a phase phi. Now, I am already anticipating the results. Again, this is a slowly varying, so this is a small parameter. Tau is a non-dimensional propagation time or length, and anticipating that I'm seeking an amplitude in front of the mode that is radially symmetric. And so if I go with these ansatz for the expansion here, then I get, by the usual thing of subability conditions, I get a couple set of equations for the amplitude, the modulated amplitude, and the phase. And I write it here. R now is the radial u squared plus v squared. C1, C2, C3 are constants that come from this subability condition. And this is a very simple linear system that in fact has an exponent, a Gaussian confinement pre-amplitude f, and the equation for the phase has a radial dependence. So in the language of wave propagation phenomenon in the linear regime, we know even in free propagation, forget about the rotation, the physics, that if we pre-chirp the pulse, the phase of the pulse, you can, even though diffraction tends to spread, if you organize your phase at the initial condition by what is called spatial chirping, then initially you can confine. So the twisting here is kind of one way to interpret this result is that the twist creates a chirp in the phase, and the chirp translates into a confinement. But this is permanent because the rotation is permanent. So the point here is that we were able to show in a similar problem these by asymptotics that indeed there is a confinement. And of interest would be a possible follow-up, what is the role of nonlinearity? So what happens when you add nonlinearity to this? I just really want to mention, I'm looking at the time, that a lot of these particular type of problems could be also studied with not on the PD wave propagation models, but as ray theory. And it's a beautiful theory to present in the sense that when you talk about ray theory, you talk about Hamiltonian optics, and there is also similarity with the least path or the path of shortest time, and the index of refraction is kind of modulate your underlying field, gravitational field. If you think about paths of particles on the action of some gravitational field. So here it is also on the action of rotation, what it is that these paths describe. In the optics, what is happening is as the rotation is changing, the rays are moving in such a way that instead of escaping eventually, they will always be coming back towards the center. And if we were to do a little bit of asymptotics, we could show that this distortion, which is parabolic-like of the index of refraction, but it's just an interesting approach to go by. I want to stay confined to the PDE way to look at these things. So that was part one. Part one is, it is in our world of the nonlinear Schrodinger equation, when you have two elements, nonlinearity and dispersion, nonlinearity and diffraction, we have now an interesting new dimensionality in what photonics can do, which is in the direction of propagation, the twist. And I highlighted briefly a couple of scenarios of why it is interesting. The second part that I also want to talk about, and similar to the first one, these are problems that I've been working on and studying with now a former student, and I'm trying to extend what we began with my former student with new people. So there is not much in terms of results, more in terms of the motivation and a few observations. So this one is interesting when you talk about it in the optics community, and it's we talk about it as the fractional nonlinear Schrodinger equation. So I refer to the fractionality as instead of having the Laplacian operator, you have a fractional power of the Laplacian. So alpha would be a parameter that can range from 0 to 2 in these studies. There is an integral operator that is the formally the same as this Laplacian, fractional Laplacian, and if you see the integral operator is non-local. This is called the Caputo integral. So we want to see first, is this interesting in a photonics context, and what could be even added? And that's where I want to go, new terms that depart from what people have studied in terms of fractional fractional Laplacian. So first, a little bit of, again, I don't have a full understanding. By no means I consider myself an expert on the connection with the probability, but I want to highlight it because it's relevant. It may be seen, maybe known by others, and it explains in some ways also why fractionality relates to a particular scaling of the medium of propagation. So when we talk about our Markov processes, we have the traditional random walk that with some probability, you just move right, left with nearest neighbors, and then you cover your, in long time, you cover a particular class of trajectories with some probability. Another one that is kind of known is the Levy flight, that you have a finite probability of making long departure, not just to nearest neighbors. And in our times, the propagation of COVID is a good example of Levy flight. When a sick patient travels from a foreign country to the US by plane, that's a Levy flight process. These are features of what would be the typical areas covering whatever would be or trajectories by random walks, the difference between the classical one and a Levy process. So if we were to do the, something, all of us at some point study the connection with of the classical random walk and diffusion, is that if we characterize this in a step in time about an update on your location by the field U at the time t plus delta t, you can move to the left, you can move to the right with some probability, or you can stay at some point. You go from the discrete to the continuous, and assuming the finiteness of the step size delta x times size delta x squared over delta t, you get the diffusion process. So classical random walk leads you to diffusion. And my point here on this perspective is Levy flights produce fractional difference, fractional Laplacian, fractional instead of fractional classical diffusion. It could be seen in the Fourier domain that if you characterize, if you do the expectation of the plane wave, the characteristic function from which typically you can extract moments. So in Fourier space, this expression goes like decaying in k as in exponentially to the minus d k to the alpha. So alpha being 2 is the classical Gaussian. The Fourier transform of a Gaussian process is also Gaussian in the Fourier. And of interest is the case where alpha is between 0 and 2. And basically the thing here is you create long tails. And the long tails also have features about some moments not converging. So an important one is alpha equals 1, where you have this well-known distribution, Lorentzian distribution. And now fractional diffusion is a problem, is a topic that has been well studied in other realms of physics. Here is a list. It's not comprehensive, but basically what makes fractionality in each of these equations is the particular, not only that the medium of propagation for the diffusion happens, for example, is not only non-homogeneous or uniform, but it has in very important non-uniformity. Imagine something with small cracks and big holes, so there is all sorts of scalings that translates in some of these models into fractional diffraction. An interesting one is the ultrasound, because they talk about it in the human body, where there is a lot of scaling and differences in terms of absorption properties of what we have inside our bodies. So of all of them, the closest for photonics is the so-called Schrodinger equation. So here is the next to last is the well-known Schrodinger equation in quantum mechanics, where you replace the square momentum operator, that's the language in quantum mechanics, by this fractional operator. Notice that this is a quantum mechanical representation. You see the h squared there. Now, the appearance of fractional Schrodinger in quantum mechanics was first proposed by Laskin in 2000. And the way you go about it, and that's in some ways a connection with this probability, these trajectories, depending on what rules you allow for movement, there is a representation of quantum mechanics by the so-called Feynman path integral. You create all sorts of possible paths from one state to the other, you assign some probability, and in the classical Markov process, it translates into the Laplacian. So Laskin did say, well, what if we create a quantum mechanics in which we allow these Levy flights, in which we allow these probabilities of long departures instead of classical Brownian motion. And that's how in 2000 he proposed the fractional Schrodinger equation. Now, as it happens in many proposals or hypotheses or conjectures in quantum mechanics, such as under-localization, parity time symmetry, you may have heard of these things. Sometimes they are hard, or they have in fact not been shown to be true, these conjectures in a quantum mechanical setting. Now, historically, one of the beauties of photonics, even though it's a classical photonics or classical optics, linear, nonlinear, is that the similarity, the equation, when you do unidirectional propagation, you have a one-to-one correspondence between the Schrodinger equation and the wave propagation equation when there is one dominant direction of propagation. So you could, it's not the first time in which people have moved a conjecture from the quantum mechanical setting to an optical setting. Now, this is again to enhance the notion of Levy flight and the non-homogeneity, not in the context of the wave propagation as a field equation, but in the concept of, again, of rays. So what is a trajectory that a ray of light will do in such a non-homogeneous medium where you have highs and lows index of refraction? Well, you have to have a medium very with this level of non-homogeneity and scaling, you know, these circles. And this was proposed in 2008 as the first example of a Levy flight of light. That's what it was called, by what was called a Levy glass. So once again, all of these things connect, whether you have ray theory to features more connected to Levy flights as trajectories with some probability, or in the collective as a wave propagation problem, it connects to the fractional Laplacian. Now, I look at my time, I want to spend less time on the details of the physics, but in 2015, there was a proposal by Longi of a resonator. A resonator is to put two mirrors and let light propagate back and forth. The idea is that's how a laser is built. And you put little elements inside this cavity. So intuitively, all I want to say to try to envision an experiment, you have natural diffraction, which is a classical k-square in wave numbers behavior. And then if you put lenses reassess the trajectories of the wave vectors. So you can have that the lens confined and then free propagation diffracts. And a cavity is an averaging process. You have very fast diffraction and confinement through the lenses many, many times. So intuitively, you could expect that in average, you can get somewhere in between free propagation and the guiding in the wave vector space, something like k to the 2 alpha, or k where alpha is between 0 and 1. So the equation here is an equation that he ends up showing. So this is the role of the lenses in the cavity that counters diffraction. And so effectively, in some sort of average sense, you create a fractional diffraction. You have guiding through some index, and then you can have gain and loss for a laser. And the idea here is, again, the novelty in this application of fractionality is depart from the classical. When you think about, when you hear about what a laser does, like your pointer that I'm not using now, is typically a love of high energy in the center. Well, doing this, fractionality can create very interesting profiles from your resonator. So I'm going to finish with a quick, and with some apologies, things about what people had talked about. Not surprising, this topic has been emerging in different proposals in the optics regime, linear and nonlinear. So I will put it in the context of some questions that we're asking classical Schrodinger equations. So one is the notion of free propagation. So this paper in 2017, what happens, how does free propagation in free space, no index, what is the role of fractionality with particular initial conditions? So, the alpha equal to 2, if you notice, is kind of the traditional one, that if the fraction is small, then it doesn't change much in shape and it stays confined. And the moment we have alpha to be less than 2, you begin to see these strong departures of some elements. I suspect in this case there is some chirping at the beginning that confines, and the level of confinement is not total, but somewhere faster that's the role of the alpha. So this is a particular example of what people think about it. An interesting thing, and that's why I mentioned collapse in the two-dimensional problem, is the question of whether collapse exists when you begin to put nonlinearity. So in the old days, you have classical diffraction, you don't have alpha as a parameter. So the idea is that the blow-up event is a combination of the number of degrees of freedom in the Laplacian and the strength of the nonlinearity. Now you have a third parameter. Are there conditions that has dimensionality, fractionality, and nonlinearity for which there is a yes-no collapse event? So that's an open question. So let me finish with a little bit of the angle we have taken. I see that my time is almost up. So a beauty about the optics is you can introduce what is called spatial temporal. So again, if you're not in the optics language, this Z would be T, and this would be Y, for example. And what we're saying is that in photonics, you can partition in a two-dimensional transverse direction in the 1 + 2. You can partition and make one fractional and one classical second derivative. So these, as far as we know, and this is work of a former student that just graduated and moved to finance, is a new direction, because you have, as alpha goes to 0, basically this is like a constant that you can phase out. You get the one-dimensional integrable nonlinear Schrodinger equation. And as alpha approaches 2, you get the 2D nonlinear Schrodinger equation. So this is a model based on physics that you can scan the role of the parameter alpha in the two worlds that I started my conversation with, one-dimensional and the two-dimensional nonlinear Schrodinger equation. So we have looked at issues such as modulational instability. We have done issues about collapse. Here is the collapse of the 2D NLS. Do we have collapse in this is a wide range of initial conditions and changes of the role of alpha. And some initial conditions, you see that the amplitude, all of these things are the peak amplitude. In some instances, you begin to see possibly collapse. As each color is different powers, and each picture is a different value of the fractional parameter alpha. So again, maybe there is a collapse arrest. These are all things that we didn't quite put in a full way to make a strong statement. So there is room to do many more here. So let me finish with the other element I mentioned. In discrete systems, as you saw throughout my presentation, in photonic systems, as you saw through my presentation, you can also have very interesting and relevant discrete systems. So the discrete version of fractionality is in fact an equation that has been studied, and the validity of the continuum limit. This is the reference I put below. And as you see, all it does is, once again, if I think about waveguides or cores where the energy is confined. Now you have the non-locality, long-range interactions. And we believe that there is ways to create these non-local interactions at the linear level. And there does the interest in connecting the discrete and continuous version and trying to learn more about these systems. So here is one simulation done by a colleague in Mexico, Luis Cisneros, to see the role again of the degree of locality. So what was alpha in the continuous is this S parameter. S is the level of non-locality. So S equal to 2 is the high S, as you can see, is the fast decay of this coupling strength. So it goes close to the discrete NLS. So here again, similar to a previous picture in the S equal to 2, you have a localized mode that propagates after spitting some radiation, but that is destroyed as the S becomes smaller. And in some instances, once again, you have fast radiation at disparate velocities as in terms of the role of the parameter S. So again, the other addition we are looking at is if we work in what is called the pulse regime, the temporal pulse regime, rather than the continuous regime, we have this other degree of freedom that we haven't even started exploring. So I think that's the spirit of PDE seminars. You talk more about what else is there, hopefully triggering interest as opposed to a polished presentation with a bunch of results. Since this is going to be recorded, and I'll be very happy to share the presentation, I end with a list of references unique to the fractional feature and some of them connected to the optics. I want to thank everyone for your attention, and I guess I can extend it even an extra 2 minutes, so I would give as much as 5 minutes with apologies again for possible presentation questions. Thank you very much to everyone.